Continue on where we have left off. I'll start as you guys get settled in with a couple, one quick comment. The quick comment being, if you remember last time I passed out one of these forms and hopefully you got one. Or did I? Okay, I thought, okay. Trying to remember if I did for this class or not. But anyways, these are the nomination forms. Again, if you have it, great. Some of you turned it into me already. Great. Just want to encourage the rest of you sometime before the month is over to think about a faculty member you think is deserving of outstanding faculty, and write that down and turn it in, remembering that myself or even Dawn are already on that list and can't be nominated. So find somebody else here. Okay. All right. So with that in mind, let's go ahead and begin where we left off. I didn't quite get as far as I had hoped, and I'll keep going. But and that's probably a little bit unfortunate because this is one of the biggest chapters of the book. I don't think it's quite as big as that chapter 9, if you remember that in Physics 121. But it's a big one, and it can go a little bit quick if you follow the similarities or the analogies I'm about to present. But even before I get to the lenses, let's finish up with the mirrors. And if you recall, we finished kind of quickly with the mirrors. I didn't get a chance to finish the discussion of the last combination, but I wanted to show you 5 combinations last time. Those 5 combinations being a flat mirror, then 3 different scenarios that can occur with the concave mirror. And so I redrew them up here. This is scenario number 1, where the object, and so this is object, and this is image. The object is beyond the center of curvature, which is twice the focal length. And what will happen is it will form an image between the focal length and the center of curvature. It will be upside down and it will be smaller. And so that makes images smaller and upside down and makes what we call real images. This scenario was very similar in this sense that the object is now here, the image is formed there. The difference being the object starts between it and the image gets projected outside. It still inverts it. In this case, the image is bigger than the object, but hopefully you can see in both cases the one further out is bigger and the one closer in is smaller, and they're of course inverted from each other. And the point of the lecture was to show you this, that those 2 scenarios mathematically are the same. The distance of the object and the distance of the image and the focal length are both related by this equation. The magnification is related by this equation. Yes?
Magnification h prime over h?
Yes. So magnification is h prime over h. How big is the image compared to the object? Okay? Then we went on towards the end of the class and we did this one. This one is certainly different looking than the other 2, but when we wrote out the equation, we ended up coming with the same mathematical relationship, that the object and image distance added, the reciprocals in them, what we call the harmonic sum of them, comes out to be the reciprocal of the focal length. And so it actually comes out to be the same equation. And so this lens, or this, mirror, we're getting to lenses today, but this mirror was a good scenario that what it would do is it would make an image that is, again, bigger in size, but right side up. And it's on this side of the mirror, so we called it a virtual image. And they're often a little bit easier to see with your eyes in the sense that if your eye is over here, the object is further away, as opposed to this one. If you looked at the one I passed around, this one's kind of hard to see at times because the image is bigger, it's close to your eye, and things that are close to you are often hard to focus on. And in fact, we'll see that at the end of the today as we talk about our lenses and our corrective lenses, our eyeglasses. I'll ask you, take some writing and move it closer and closer and closer and closer, and at some point you can't focus on it anymore. Now you guys are young, so it's probably pretty close compared to you know. All right. But you know how close it is will tell you something about the the quality of the lens of your eye there, and so that's kind of that scenario. But in any case, what I wanted you to see is that the three up here, and also with the flat mirror, all obey the same relationship. That's what I wanted to emphasize. All 10 different cases we're going to see this chapter fit that equation. If, and here's kind of the catch, so I'm going to put it back here on the board, if we're willing to follow this sign convention. Okay? And here's what we mean by that. We saw the first sign convention back here when we did our geometry, and again, not repeat the geometry, but when we did that geometry, we came up with two sets of similar triangles. We drew one set in one color. I'll just draw it today in black. We drew another set in blue, and I'll just draw the triangles. But when we wrote out the geometry, we came up with something that really wasn't quite like this. It was actually the negative of this. And we changed the sign because we said if we're willing to take h prime as a negative number, then we would have this relationship. And so we said that sometimes the height of the image will be treated as a positive number, and other times it will be treated as a negative number. And so we must treat h prime as a negative number here and a negative number here. But we must treat h prime as a positive number here in order for them to have those equations. And so again, the big advantage is you don't have a whole series of different scenarios to remember and equations to remember or to derive. You just have one set. What you have to remember is that you need to choose h to be positive or negative. But fortunately, I think that one's pretty obvious. That one is, look, well, it's upside down, so I'll treat down as negative and up as positive. Fair enough. And it works out great. And in fact, not only is it easy kind of to remember that one, but it's also pretty easy to then use it in the calculations. And if you do a calculation and come up with a negative h prime, what does that tell you? It's upside down. And so it's really not a disadvantage, it's really an advantage. It tells you something about the physics that's going on, the pluses and minuses. Just like we did with forces and accelerations, the pluses and minuses to the forces give us some valuable information. And so you'll see that you'll really appreciate these two equations because they apply to all the scenario of the mirrors. And what we'll see today, it applies to all the scenarios of the lenses. We just have to remember what we mean by positive and negative. All right? Well, also we saw in this one, this was, I think, a little harder one to see than this, but when we wrote out the triangles for this one, we did discover that the only way we can make these equations simple match is if we choose, do you remember this one? What was the key here to this one? Yeah, Q is what? Negative, less than 0. Okay? And so like I said, we started off with this scenario and we essentially treated everything positive except for h prime. But for it to work out in this scenario, we had to choose Q to be negative. And so the convention we come up with is saying, look, you still want to use this equation for this scenario, fine, you can just call Q negative when it's on that side. And so you'll see here that we had this image location. And we said if it's in front of the mirror, in other words, if it's a real image, then treat Q as a positive. But if it is behind the mirror, if it is on the virtual side, treat Q as a negative. So again, one of the most important things I think I can do here is not so much keep drawing these rays, although I do think that's important and coming up with the equations, but to remind you that these are the equations that will work. Whether I completely prove it or not, I want to emphasize this is the equation will work, and what I need to emphasize is this then will be our sign convention that will make it work for all 10 cases, the 5 different mirror cases and the 5 different lens cases that we'll be looking at in this chapter. Okay? And so you've got to commit this to memory. Now fortunately, hopefully it's not too hard. As I said, for me, memorizing that H is positive when it's up and H is negative when it's down is not too bad. That's like, okay, that's just kind of a no-brainer to me. This one might take a little bit of thought to remember, okay, which side is positive and which side is negative. But let me tell you how it works for me. The positive side is where the light really is. That's the thing to remember. Because in the mirror, you can see that the light came in, it hit the mirror and bounced off. It's why we drew this scenario first. This represents the positive Q. So where the light really does go to, which is why we call it the real side of the mirror, because it owed to form real images on that side. The light really is there. But a scenario like this, the light is not really back here. It has the appearance of coming from here. So that's why we called it a virtual image. And so the virtual images correspond to negative positions. And that's how I remember. Well, the light's not really there. So, okay, if the light's not there, that's why we treat it as the negative. And I don't know if that works so well, but somehow you need to remember when it is positive and negative, and then use when you solve the solutions for positive and negative. Because they do get more complicated here, as we see in this next and last mirror, and then as we see in the lenses. And so you'll need some kind of way to kind of keep that in mind. When is it positive, when is it negative? And like I said, fortunately, it's the same equation. All right? But let's do this one. And I'll start off today with putting a mirror that is concaved out this way. And we finished the lecture with me kind of just rushing the answer. What kind of image do you get?
Smaller.
Yeah, smaller and right side up, right? The fourth combination. So of the 4 combinations we can have, bigger, smaller? Upside down? Erect? Of those 4 combinations, we've done 3 of them. The one that's missing is erect and smaller, right? And this mirror will do it. And so you can see it here. If I come over here to my laser box again, and turn this on, power down the lights there, and say, okay, what happens to the light when it hits something that is curved outward towards you? Convex. And so the convex mirror, probably not too much of a surprise, instead of making the light converge inward, it makes the light diverge. And so it spreads out. But here's an interesting pattern. If you were standing over here and you were to trace these rays back, they appear to be coming from a spot right there. Now, that is sort of, not exactly the same, I agree, but it is sort of like this one here. This one, we said the light would come back and get focused right there. And then beyond that, look what happens to the light. Doesn't it spread out? And so somebody standing over here would have the appearance that the light is coming from that spot. And I would say it really is. So we'll call that a real focal point. I didn't use the word real focal point before, but that is a real focal point, meaning the light is on the real side, meaning the light really did converge at that point. But when I take this mirror away and I put that one there, what would this person over here see? What we are going to call a virtual focal point. Now, I'm not ever saying that the light really did focus there, but it has that same appearance from somebody standing beyond it, as if the light was coming from that spot. And so, if I turn these lights back on here, this mirror, too, has a focal point. Now, to be a little more specific, we should probably call it a virtual focal point. But if we throw off that word, everybody knows then that the concave focal point and the convex focal point are kind of different, but kind of the same, right? And so let's see what would happen if you put an object in front of a mirror like this, knowing the same patterns that we did here. So let's repeat what we did on Tuesday and say, okay, here comes the light. The light comes in and hits the mirror. The one coming parallel would go up, down, up, as if it was coming from the virtual focal point, right? That's how we would draw it. And so, looking at these, we would need to draw a second one. Of course, the second one we drew was through the focal point. Well, can't really draw one through the focal point. It doesn't really go through the focal point, right? The light never really goes on that side of the mirror. It reflects. That's why we called it a mirror. All right, so what's the second one? Yeah, again, it is the reverse of this. But if there was a ray headed in the same direction, it's kind of like this one here. We drew the second ray, not going through the focal point, but heading as if it went through it. This one I'm drawing as if it's going to there, because what would happen to it? It would bounce off and go parallel. And so that's the reverse process. So again, somebody standing over here would say, what about those two rays? Now, this ray would appear to come from somewhere back here. This ray would appear to come somewhere back here. They cross right there, and so the person would say that right here is an image. And that arrowhead, and then we could do like we did on Tuesday, we could say the middle of it and the bottom of it and say, okay, that's where the image appears to be. And so you'll see that that image is smaller than the object, right, and right side up. And more than that, you'll see that you would get the same thing no matter where you put your object on the outside. It's not like these where you can actually move in front of the focal point. You can't do that when the mirror is angled like this. You can't pass it. You're always just at one spot. So that's why I had said earlier, this is the boring mirror, in the sense it only does one thing. It makes a virtual image. It makes an image that is smaller than the object. That's all it ever does. Right side up. That's all it can do. And again, the more interesting ones, I think, are the ones that we have some options with. Not to say it's not useful, as we talked about before, and I noticed we mentioned one with the passenger side view mirror, and then I noticed that your author has a good picture of that. Just, I guess, in case you've never seen the side mirror on your car there, but it shows it really well, yeah.
You did, from what I can tell here, you said that it's like if bigger image is usually a virtual image.
The bigger one is, no.
Oh, you know what that?
This is bigger and virtual. This is bigger and real. So bigger doesn't mean real or virtual.
Oh, okay, so it's possible to get bigger and right side up, or is it always right side up?
Bigger and right side up is right here.
If you want, like you said something about the Disney ghost house, if you have those ghosts dancing around through the tables, how do you project them?
Right here.
So
Bigger and real.
So those images are actually upside down.
Yeah. So I guess I should have emphasized. Those little carvings of the ghosts are upside down dancing. So when they project them and you see them, the ghosts don't look upside down. Yeah. Right. And that's no different than a movie projector, although in today's digital age, maybe you guys aren't familiar with putting slides or film into a projector. But when you project it onto the screen, you know, if you've got this wonderful picture of your trip to Yosemite and you want to show the world, look, here's a picture of Half Dome, and you would put it in the slide projector, you would look at it, oh yeah, this is Half Dome. You would turn it upside down, you'd put it in the projector, so when it displays on the screen, what happens? Yeah, and I don't know if you maybe, I don't know if time has gone far enough. Have you guys ever seen just a slideshow? Slides? All right. And have you ever gone through it and every once in a while one's upside down? No? Some of you, yeah. It's common to accidentally get it up, because if you're the presenter, you go, oh, I want to do this one, and then this one. But you got to remember to put it in upside down. Oh, and then this one. Oh, this is a good one. And you just forget to put it in upside down. And so now you're going through the slideshow. Oh, look, here's Half Dome. Oh, here's a bear. Here's Yosemite Falls. Oh, here's Bridal. Oh, it's upside down. You know, and so you just forget. But that's what you're pointing out. So yes, it would be upside down. And so, like if I said, if you go to an older theater where they actually use old film, Of course, you want to see it right side up, but if you go into the booth up there, you'll see that they are feeding the film there, and the film, the slides in the film are upside down. The frames of the film are upside down. Yeah, because it's going to invert it. And I should point out, since you want the light to hit the screen, you want this. You want a real image. You don't want this. This is bigger, but it's virtual. You can't display this on a screen. You can't put a movie screen right here and say, hey, see the image? No, you can. The light's not really there. Now, you could stand back here and say, can you see the image? Yes, I can see it as it goes into my eye, because my eye focuses on it as if it's coming from here. But I can't put a screen there and have the actual light hit there. So the movie screen is going to have to be this real image. And again, this is probably a bad example because this is mirrors and they use lenses, which is what we're getting to, not mirrors. But we could do it with mirrors, but it makes sense to do it with lenses here. Anyways, in the interest of hopefully a little bit of time, let me go kind of quick here. But if I were to draw a black set of triangles like this and write the height of the image is to the height of the object as, and I guess it would have to be this distance, and maybe I need to put some notation on here, this would be that virtual focal length. Whereas this distance would be the image distance, so there's Q, and this distance would be the object distance, so there's my P. So again, remember, everything's measured from the mirror, okay? But when you write this out, you would say that height of the image is to the height of the object as focal length is to focal length plus object distance, right? Except when I just did that geometry like I did on Tuesday, don't I really mean absolute values there? And eventually I want this equation to look like that equation. How could I get this equation to look like that equation? What if I define the focal length on the other side of the mirror as a negative number? So in other words, when I do my geometry, I really mean absolute values. So when I get rid of the absolute values, I really mean this. And as I do my arithmetic, this becomes an F minus a P. And that equation then does match that equation, which if I get the other equation to match that one, then that one and that one will be valid. And so notice here that this equation does work if I'm willing to do what? Watch my signs and call F a negative number here. And so our next one in this chart is to remember that the focal length, and then also the radius, because since the focal length is half the radius, could be defined as a positive number, as we've been doing for the concave mirror, but we could also do a convex mirror. So again, we need to remember that as we put it into the equation. If the problem says you have a convex mirror, find the location of the image, and you go to do the math, you better make sure you put F in as a negative number. Okay, they probably won't tell you it's a negative number. They'll just say it's a convex mirror. Convex mirror with a focal length of 10. But what that means to you is you got to put it in as a negative number. And that's my warning for you. Make sure that you do. And then you can use all these equations all you want. But if you don't call F a negative number, those equations won't work. Okay? So that's the principle. And please keep in mind, for whatever reason, I've had students every year ask me a simple question: how in the world can a radius be negative? No, I'm not saying the distance is negative. That's not what I mean. What I just mean is to make this convenient, I'll pick a side. And again, notice it's the same side. It's the virtual side. So calling Q negative and the focal length negative is, you know, the side the light doesn't go to fits the pattern. So that's how I remember it. Hey, the light didn't go there. So that's the Q of a negative side. That's the F of a negative side. That's the R of the negative side. The virtual side, that's the side that has all the negatives. Yeah.
When you said focal length 10, you mean 10 units or something?
Yeah, like 10 centimeters, 10 inches, 10, yeah. Yeah, yeah.
Magnification doesn't have units, does it?
Oh, right, and fair enough. Magnification is a ratio of sizes. So meters to meters, centimeters to centimeters, inches to inches. Yeah, so no units. It's just how many times bigger is it? It's 3 times bigger. Or it's only 1/3 as big. Now it could be negative. It could be negative 1/3, which would tell me it's upside down and smaller. Whereas a negative 3 would tell me it's upside down and bigger. Yeah, yeah. So I certainly would have a sign with it. By the way, as long as I'm here, I might as well throw this in. This is often referred to then as the power of the mirror, the reciprocal of it. Okay? And if you look at the units here, the units would be inverse meters. And so we'll talk about how powerful is your mirror. And what you mean is a powerful mirror means it has a small focal length. That makes sense. The power is, how does it bring the light into a focus? Yeah, a couple more.
Since P can be treated positive or negative, why don't you have absolute value for it?
You will notice that everything can be either positive or negative. And so far, I have shown you when H is positive and negative, when the magnification is positive and negative. Then I showed you when Q is positive, negative. And now today I'm showing you when F is positive and negative. But I think the hardest one to get is when is P going to be negative? When the object is behind the mirror? What? How do you even get light to hit the mirror if it's behind the mirror? Hold on. All right, we're getting to that. That's the one I'm doing last for just this reason. Yeah.
So if you have a piece of a cylinder rather than a piece of a sphere,
Oh, yeah.
here,
Good.
how can you define magnification the same way? Because only one side,
Okay.
one axis is getting.
So we would have a magnification in the y direction and a magnification in the x direction. And so if it's a cylinder, depends how you hold the cylinder, but let's say, the cylinder's this way. And so I'm holding a round cylinder in front of me like this. Left and right, there's no curvature to it. So it's like a flat mirror. So my magnification is just 1. And so when I look at it, my shoulders are the same part away. But the curvature here would give me a magnification, so my height would change.
Is it just implied and we just call it M, or do you have to specify M, Y, or that?
Again, I would say at this level, being an introductory class, we are really just using the x direction to be the position and the vertical direction to be the magnification. But the real world, as you're pointing out, would have this. And so not so much this semester, but there's a couple of tricky problems coming up here that will make you think about that. But for the most part, we don't call magnification X and magnification Y. But later on, yes. So you're going down the right road. We would have M sub X and M sub Y for how much did it magnify. Yeah. Worse still, I hate to bring this up, I got it now, is what a magnification in the Z?
What would that be like?
So if I put a box out here, okay, now it's 3 dimensions, it's a cube, okay, but if this thing has a spherical curvature, you would agree that the image, and so this one would form an image right in here somewhere, okay? And so up and down and left and right would have the same magnification. But the front edge would be here. The back edge would be here. The back edge being further away, meaning P is a little bit bigger. And the magnification is related to where P and Q is. The back of the box is not magnified the same as the front of the box. So the box now reverses order. And the back of the box has a smaller size than the front of the box. And the image I see is a magnification in the Z direction. The size this way is not the size this way. And it's not even the shape of a box anymore. It's a trapezoid. But getting beyond the fundamentals here and getting into that. But you would have a magnification X, magnification Y, magnification Z, and what you would call in math a transformation of its shape.
So the Z wouldn't even be a constant number, it would be
No.
an equation.
Oh yeah, yeah, sure. Because it would depend on position.
So that would have units then.
Yeah, but the magnification in the x and y also depend on position too, right? Because it depends on the ratio. And
The Z magnification would have units.
no, eventually it would not have any units. But I would say the magnification at some point has to, I would call it a magnification field is probably the best way to describe it. I would say the magnification is different at each point, but it's still unitless. Well, yeah, definitely got way off track there. All right, let's come back to here. So you saw that. Let me also do the other triangle. Here's the other triangle. What I can do is, like we saw before, I can draw a blue triangle in here. And again, if I write this out, I can say the height of the image is to the height of the object. So height of the image is to the height of the object as this distance, which I would call this F minus Q. But I'll pause there because when I do the geometry, what I really mean is the magnitude of F and the magnitude of Q. Both of those of which I have already referred to as a negative number when I'm doing my optics. So I'm going to put absolute value there for a moment. And then over my F, which again, as we just argued in the first step, that I would call this a negative number as I am doing my optics. And so if we actually then think about our absolute values and go from geometry and algebra and actually change this, this would be a negative F. This would be negative of a negative Q. This would be a negative of an F. And as we simplify this, the two negatives there become a positive. As we feed this negative up to here, that becomes a positive, that becomes a negative, and sure enough, it does match the second equation. So again, if we're willing to call Q and F a negative number when we're over here on the virtual side, we are able to get the same set of equations here which lead to this, and therefore we have the same set of equations regardless of whether we have a concave mirror or whether we have a convex mirror. And again, that's what I keep emphasizing. I must have said it half a dozen times by now, and I don't know if I can even say it more than that, and if you don't hear it now, it's just not going to sink in. But that is really the key, is to realize that, hey, good news here. This works, regardless of it. In fact, the signs are really great, because if you go through a problem and you do all the arithmetic, and you come to the end of the problem, and you come up and you calculate, it says calculate for F, and you finish the problem, and F is a negative number, what does it tell you? Tell you the type of mirror you have, right? You said you have a convex mirror here. And that may actually be the question. The question may actually be, hey, you want to get this accomplished. Here's what you want to do. You want to place the object 10 centimeters away. You want to make it 3 times bigger. You want it to be upside down. That's what you want. You put in the math and you calculate out, and it comes out to be F, a negative number. What it tells you is you want it to be a convex. Although that was a bad choice, because 3 times bigger is never going to happen with convex. So, but 3 times smaller, okay, a third of its size. But if you went through all that math there and you got then a negative number, that would tell you something. So again, remember these. All right, finally, and then we can leave mirrors and go to lenses. I think we've covered everything except P. Plus or minus here, plus or minus here, plus or minus here, plus or minus here. How in the world are you going to get a minus P? What does a minus P mean? Well, let's see if I can draw a picture. Minus P's you will never see unless you have more than one mirror. That's the good news. So you can't get a negative P in any of the scenarios that I have now shown you. Let's do this for a moment. Let me come over here and do this. Let's say I have a concave mirror that has a focal length, F, of 10 centimeters. And I go ahead and I put an object at 15 centimeters. But then I put another mirror, maybe a flat mirror here. What will happen? Well, 10 and 10 make 20. How are you going to handle 2 mirrors? 3, 4, 5, infinite. And fortunately, it's really the same thing that you probably did in grade school. If you learn to add 2 numbers together, can you add 3? I mean, what do? You first find the answer to those 2, and then you put that together. And you always do one by one. So here's the logic. The logic being here that, let's just forget this mirror for a moment. If I wasn't even thinking about that mirror, what would happen is the light would go like this case, and go through the focal point, and then go through the focal point, and go out to here. And it would form an image right there. Fair enough? And just like this little silly example is trying to say, what am I going to do next to figure out where the image is for this one? Answer? Forget you have this mirror. The whole thing between this object and this mirror was to control the light and redirect it as if the light is coming from here. And so the image from the first mirror now becomes the object for the second one. And so I'll just say, hey, I'm not even going to worry about that mirror. I'm just going to ask, what would the image in this flat mirror look like from that one? Of course, you know that there's not really an object here. But what you do know is the reason it looks like an object is because the light has been redirected by the mirror in such a pattern that it will form right there. So, as I kind of corny example here was saying, all we have to do is know how to operate one mirror. And once we get the image of that first one, that becomes now the object for the next one. And I put some actual concrete numbers up here so I can actually give us something to work with. And so if I was just ignoring, well, actually, let me finish my picture. Where would the image then of this object? Now, I've got to be careful. When I say object, I mean the object to the second mirror. It's the image that is formed from the first mirror. And so the image from the first mirror becomes now the object for the second one. And we learned that flat mirrors, the object and image distance are exactly the same. The magnification is 1, and so the first mirror inverted it, and then the second mirror doesn't change that inversion, keeps it the way it is, and gives it an image back here. Now, of course, for somebody to see it, the light would have to be doing this. The light would hit here and bounce back. The light would hit here and, I'm out of room. Draw on the wall there, it would look there. And if I were to trace these rays back, that's where it would appear to come from. And so somebody standing here looking into that mirror is getting the light from it starting here, hitting that mirror, and then getting to the person's eyes. And what they would see is directed back to here. And I would call that then the final image. Image number 2. And so I think you're seeing the strategy here. All I need to teach you is how to handle one mirror. And then you can do 2 or 3 or 4 or 5. Of course, now, please remember, I still have not explained how in the world is p going to be a negative number? But I'm hopefully getting there. Because if I was actually doing this problem, this would make a good example. Because I'm not sure how much time I will have to do examples today. And I go, well, before I even get to the lens, let me do at least one example for a mirror. And a double mirror is probably a good one, because that's the most advanced. So if I was starting here, the first thing I would do is get out my calculator and say 1 over f is equal to 1 over p plus 1 over q. And from that, I should be able to find q. Keeping in mind my signs. So I have told you the focal length is 10. Positive number or negative number? Positive. Why? It's on the real side. It is, as they saw up there in the chart, it is a concave. So this would be a 1 over 10. What's my object distance? Okay, I gave you 15. And the unknown here is the q. And so it would be 1 over 10 minus 1 over 15, and then take the reciprocal of that. And if it helps, I particularly really like that reciprocal button that is on your calculator there. Okay, and this is an 83, and it has it right in the middle there, because I could just easily go 10 reciprocal minus 15 reciprocal, enter reciprocal, enter 30. And so it makes short work of what we call harmonic sums, and so it's got that reciprocal. Now some calculators have the reciprocal after you have to hit a shift, and I hate those calculators. I just use the reciprocal so much. If I got to do a shift, I mean, it's just like the end of the world, right? One more button. I don't know why that bothers me, but nonetheless, I'm going to come up with a number, and in this case, I get 30 centimeters. And so this distance here is 30 centimeters, not a perfect drawing to scale, but that should be 30 from the mirror. And I can do a magnification. What is the magnification of it? Well, that would be a minus q over a p. In this case, the q I just solved as a 30 centimeters. And the p was a 15. And so the magnification is -2, which means what to me? Yeah, upside down because of negative, and twice as big because of the 2. And so sure enough, it does match my picture really well. And so that's the first example I can do, and probably the easiest one, where it's just one mirror. But let me extend that a little bit. Because what if I also told you that these two mirrors were placed 50 centimeters apart? And our goal was to find then the final image, meaning this, that the image from the first one now becomes the object for the second one. So if I clear this off a little bit, and I'll even clear this off for a moment. Myself a little more room till we get to the lenses. But let's do the second half of this, which is then to say, where's the final image? And I would do all this again. I have a mirror. So 1 over f equals 1 over p, 1 over q. Oh wait, that only works for the concave mirror, right? Oh, concave and convex, but I got a flat mirror. It works for all of them. Again, you're willing to pay attention to those signs, it'll work for all of them. So let's give this one a try. What's the focal length for a flat mirror? Yeah, the focal length is half the radius of curvature, as we said, for any mirror. And so something that looks flat is because its radius is infinitely big. Very, very, very big. So we can say this is very, very big. So what is 1 over very, very big? 0. So 0 equals 1 over p plus 1 over q for this second mirror. Which is actually kind of nice, because when I solve this, I can get p equals -q, right? That's what that says. And of course, that's exactly what we did. The easy case, we said that the distance of the image and the distance of the object were exactly the same, except that the object is behind the mirror. And when we did the flat mirror on Tuesday, we hadn't even talked about positive and negatives, but now we see that, of course, they should be opposite here. And so as I apply this, this becomes my question now. What is p? What is the value of p? And I should emphasize, for the second mirror. Because the value of p for the first mirror was 15, right? But what I want to know is how far away is this? Let's just talk about absolute value for a moment. How far is this? All right, so you've already figured out, hopefully, that this distance is 30. So what's this? 20. Okay? So can I at least say the absolute value of P is 20? And I'll do you one better. This is not the case of a negative P. This is a positive P. I still haven't got to the negative case that I'm trying to work up for. But let's look closely at this. When is P positive and negative? Well, it's positive when it is in front of the mirror. Now let's think closely about what we mean by front of the mirror. Because notice it didn't say left of the mirror. And unfortunately, or maybe fortunately, every case I gave you was the same in the sense that you almost begin to think that everything on this side was positive and everything on that side was negative. But that's not what we meant. What did we mean by positives? The side the light is on, right? The side of the light is on is what we call the positive side of the mirror. So I really have, except it's going that way, the same as if it was going that way, right? I really have light in front of the mirror. And so just because the direction has switched, that doesn't give me a negative P. And that's what I wanted you to see. That is not a negative P. This is still a positive P. This image from the first mirror, which is now becoming the object for the second mirror, is in front of the mirror. And its distance is 20. So again, notice I don't use the 15. Notice I don't use the 30. Notice I don't use the 50. What I do is, how far is it from the mirror? And that's where the common mistakes are made. Students will use all kinds of different values for P, but P simply means how far is the object from that mirror. And in this case, my object is the image from the first mirror. And it is 20, and it is still considered in front. So knowing that, P becomes a 20, and then Q becomes a negative 20. And of course the magnification for the second mirror, so maybe I'll even put a little 2 here, because maybe I should put a 1 there. That's the magnification of the first mirror. And the magnification of the second mirror is minus Q over P, which doesn't surprise you. It comes out to be 1. That's what we've been saying. And so this image over here is the same size as that. It's 20 away here, it's 20 away there. And notice it's on the backside of the mirror, right? Q is negative. We called Q, where's Q? Q right here. We call Q negative when it's on the virtual side, when it's on the side where the light doesn't exist, where the light appears to be coming from. And so this is my negative 20. Now, if we ultimately are asking this question, where is its position and how big is it, or how much is it magnified or reduced, I would have just figured out its position. Its position is 20 from that mirror. And it depends how they word the question. Do they want to know how far it is from this mirror? Well, that one's easy. It's 20. If they want to know how far is it from its original object, well, I guess I would take the 20 and add another 35. Right? Because that's 15 and that whole thing's 50, so that must be 35. And so the image that is formed is 30 and, what did I say, 30 and 20, 55 from that one. Okay? And so again, you need to draw some pictures, you need to draw some geometry, and probably more than any other chapter you've probably seen as you did the reading is they've got all these drawings, they've got all these pictures, and I would encourage you to do them too. Draw these rays. Give yourself a good conceptual picture of what's going on to make sure that the math corresponds to that. And of course the other question is, how big is this? How big is this one compared to that one? Now maybe this isn't a good example for that because the second mirror didn't change its magnification, but I would want to say this, that the total size of it would be how much bigger or smaller did we make it the first time, times how much bigger and smaller did we make it the second time. So the first case we made it a negative 2 times, and the next time we made it 1, and so the total magnification is twice as big but upside down. And of course that really all occurred, its size changed all occurred from just one mirror, but this could have been another concave or a convex mirror, and that would have had a number other than 1 for the magnification. But you would have done exactly the same logic, just the numbers would have been different. All right, so my first goal here was to show you that this does not give us a negative P. This is still a positive P. So how do I get a negative P?
Would you put that mirror in between the object and the...
Exactly. So here's what I'm after. This is why I said the negative P is the hardest one to get. I think this picture hopefully will illustrate it. That's why I went through it. But the only way to get a negative P is to have a second mirror. And that is because it says your object has to be behind the mirror. You can't get the object behind the mirror when you have just one mirror, but you can, and maybe I'll change it with a blue line. What if instead of putting the mirror here, I had put the mirror at the center of curvature, meaning it is 20 centimeters. Now again, see the logic? What is the object for the second mirror? The image from the first one. But where is the image from the first one? Behind the mirror. Exactly. And so hence we call it a virtual object, because you've actually put the second mirror, you're actually redirecting the light before you can ever really focus the light. And so the virtual seems to make a perfect name for it, a virtual object. So things that you hold in your hands can never be virtual objects. The light comes from them. You have to shine the light onto a mirror, which would then form an image. And then, of course, you would have to put the next mirror before that image can get formed, not after, and it's diverging away. The light is still converging. So like I said, this is probably the hardest one, really, to understand. But yes, P can be a negative number. It'll just take a second or third, fourth, fifth mirror or lens. Yeah.
So there's also another image forming here, right? What about the initial object's image in the first mirror?
Ah, I'm glad you asked that, because that's my next step. But let me just keep going here, okay? Let me go ahead and just do the negative P for a second, and what would change in this problem. And what I really want you to see is the calculations for the first one don't change, right? What I do in the first mirror is I find out what is the position and what is the magnification of this real object, which is now forming this image. And without this mirror, I would even call this a real image. But what's going to happen is before this image can form, before I get the real image, the mirror here reflects the light and redirects it. And so this distance is what we are going to refer to then as the negative P. How far is this from our mirror? So if I come over here and erase this second calculation, I guess I don't have to erase too much. But if I still treat it as a flat mirror, I would say its focal length is infinity, 1 over infinity is 0, and then that gives me, again, P equals negative Q. That's always true for a flat mirror. But in this case, what is the value of P? Well, we just came up with the idea from the first mirror that this is 30. And I'm telling you this second mirror is placed at the center of curvature, which is 20. So how far is this? That's magnitude, it's 10, right? But when I put it over here into the equation, I would call it a negative 10. Okay? And that's this one right there. That yes, you can have a virtual object. Okay? So, by the way, what does that say about Q? It's what? Positive 10. Ooh. Positive. What does positive mean?
Real image.
I get a real image with a flat mirror.
Because the object was virtual.
I told you, these first cases I drew where it sounded so simple, like the convex always gives you a virtual, the flat always gives you a virtual. That was all based on P being positive. Now if P becomes negative, guess what's going to happen? It's all going to switch roles. And so this flat mirror that always gave me a virtual image may not. Let's draw the rays so we can see it. But this convex mirror that always gave me a virtual and smaller may not, when it is the second mirror in the system. That negative p can change everything in the equation. And I think you can see it in the drawing if I draw it something like this. Now it looks like my blue line didn't show up real well. Let me draw it a little darker there. There's the blue one. This ray would have been formed right there. So it's probably best to change my drawing into a dotted line there, because we like to represent the dotted line of where the light would have gone had it gone there. But see, now that I'm hitting this mirror, it doesn't go there. So where does it go instead? Yeah, well, this ray comes right back onto itself. And this ray bounces off the mirror and meets right there. So there's where the image is formed. And where is it? Real side. How far? Ten. Right? And so it does form the real image. The light is still coming together. All we did was hit the mirror and ricochet off. So, again, careful with this negative. It can happen. Careful when you have multiple mirrors. Let's extend this a little bit. Your question's a great one. Yeah?
How would anyone see that?
Well, okay. And actually, I'm glad you brought that up. You could be standing in the middle here, right? No. Now, granted, you would block some of the light. So maybe, and you would be blocking the one that I've drawn. I was going to say, maybe that's a bad place to stand. But no, it's not. It hopefully will illustrate. Yes, I would block this light. Fair enough? But remember, I'm just drawing two of all the rays. So this ray, I mean, there would be other rays, like this one. Bing, bing, bing. And there would be this ray. Bing, bing, bing. And so all the rays that hit this part of the mirror would go and hit that mirror and then come to here. And even most of those wouldn't even go to my eyes. Some would go down to my feet and here. And so if I had a pet dog with me, that dog would still see the image and I would see the image. And so as I look into that mirror, I am going to say that I have an image, a real image in front of me because of that flat mirror. Yeah. And so I have it. Now, I think what also you are asking, and it's what you asked, is this is not the end of the story. Because if the light goes from the first mirror into the second, what else does it do? It goes back into the first. Which then goes back and goes back and goes back. And so as I stand between two mirrors, what am I going to see?
A lot of images.
A lot of images. I would see the first reflection off the mirror, then 3 reflections, then 5 reflections, then 7 reflections. But let's just do the 3. So, again, maybe I should clean this up a little bit and say, all right. This is the focal point, and that's there, and my object is halfway out. It would bounce off, go through the focal point, dot, dot, dot. It would go through the focal point, hit the mirror, go back, dot, dot, dot. Right? And so, hang on here, bummer. This is not going to come out to be some good numbers. Why don't I put my flat mirror just a little bit further back? How about that? I just happened to pick a terrible number that would not have a mathematical solution when we look at the third mirror. Bummer. And I didn't want that to happen. Okay. All right. So I'm going to change that number here. And I heard somebody say, well, where's the third mirror? Answer. It's the first one. Right? What's going to happen is the light's going to go into the first, bounce into the second, bounce back to the third, and come back. And so if you are standing in between the mirrors here, but looking that way, you will see the light come towards you in that third reflection. Right? You will get an image. And what will you get? And maybe I should get this person out of the way, because let me just do the second one again. The first calculation is still this. The first calculation would still put the image from the first one here. It would put the magnification at -2. The flat mirror would still look like this, but I am changing the numbers here a little bit, because I've moved the mirror now so that it's 25 away. So what would be the value of P? Negative is what I'm after. And it's a -5 in this case. So again, the 30 means how far away is it from the mirror and the image from this mirror. But then the second calculation becomes object distance, and that's how far away is it from this mirror, which magnitude is 5, but it's on this side, so it's a -5. It's a virtual object. Which of course means my Q becomes a +5. And so the scenario I have looks a lot like we just saw, where the light bounces back and bounces down, and so here would be the image that is formed from the second one. And the light really does converge here, and hence Q becomes a positive number. But now this light, now again, maybe these are bad rays to draw, because this ray goes to here. This ray is going here, which in my picture actually misses the mirror itself. So these two rays that I have used successfully for the first two mirrors don't really make a good option. But remember this, when these two rays meet here, all the rays meet here. So you could think about light coming in every direction from that point. So as I think about the light coming from this image of the second one, it's going to go into that mirror representing my third one. And so I will draw this ray. In fact, maybe I'll even change colors if that will help you see it better. But if I draw the ray that's coming this one, which this is one of the original two I was drawing, it would bounce off and go that. And there's many other rays I can draw, but this one down here is going to be useless at this point, so it serves me well for the first two. But instead, I'm going to draw the one that goes through the focal point. It's the mirror, and goes that way. And so this one is going to form an image right there. Yeah.
So that ray that you just drew,
The orange one?
yeah, where would that originally come from?
Oh, now, okay. Now, like I said, it's pretty easy to draw it here, but as you're saying, it's got to originally come from here, right? So, okay, so if it's coming this way, it must have come from here, right? Which means it must have come from here. Now, again, doesn't really show it. If the mirror was that big, it would have come from there. That's the light coming from the tip of that arrowhead, hitting the curved mirror, off of that mirror, forming an image there, going back into the mirror, forming a third image.
That makes more sense with the bigger.
Yeah, now of course remember, I don't really have that ray hitting, but all the other rays, some would. And so I'm just drawing one that would be possible because I know how to draw it and calculate it. But even if that one's not really hitting the mirror, if the mirror's not that big, there are parts that would hit it. And so I would still get the same thing. So, yeah.
Why do we always choose this side? The light's always going towards the concave mirror first and not to the flat mirror.
It's doing both. Yeah, it's doing both. So when I ask the question, what am I going to see when I stand inside of this mirror? Okay, it kind of depends where I'm standing and what direction I'm looking. Okay, so when I did the two, I was implying that I was standing in the middle looking into the flat mirror because the light had come and hit the concave and then went to the flat and then came to me. But now I'm kind of implying that I'm standing in the middle looking at the concave because the light is going to go to the concave, to the flat, back to the concave, and come to me. And so, and you can see it keeps ricocheting back around, and I get an infinite number of images here. But I will only see half of an infinite because I will only be looking at one direction or the other. And I guess what's half of infinity? Infinity. What's a third of infinity? What's a fifth of infinity? So here's a good math question. How many infinities are there? There's an infinite number of infinities, right? Because you can take half of infinities, and that's a different number, but it's still an infinite. Not a good question to throw at scientists and engineers, but mathematicians love it. Oh my gosh. There's an infinite number of infinities. So, you want to have fun, ask your math teacher, how many infinities are there? He or she will have a field day on that one. I mean, you'll get sidetracked for 10 minutes easily off that one. You know, it's like, oh, hey, we'll get off track here. This will be fun. All right. But, oh, yeah. Infinite number of infinities. Or how many prime numbers are there? Infinite? Uh-huh.
That's yet to be proven.
But how do you show that there's a proof? Oh, there's a fun one, too. And why do we care about prime numbers? Well, because everything can be built from prime numbers. So really all we need to know is prime numbers. We don't really care about the number 10. It's the 2 and the 5, right? Because everything can be written as the 2 and the 5. Some of the primes. So we could break any computer code because we don't need to know all the numbers. We just need to know the prime numbers. Wasn't there there was an old science fiction one, the Sneakers. It was really bad and old, so okay, you guys probably didn't see it because it's not worth seeing. But anyway, that's what the whole movie was based on. These two young Russians figured out how to calculate found out all the prime numbers, and therefore you can crack any numbers, and then you can break into the Pentagon and all the national security, because there's no security anymore. Listen to me. Say your math teacher will get lost. I'm getting lost in the math. All right. Did I take another question? Yeah. Okay. Yeah.
If you were the object, the very first object, you would be looking at the mirror, at the concave mirror, and then the image would go back and hit the flat mirror. But isn't the image that comes is that the third image that could be actually behind you, so you wouldn't see like anything. I mean, it wouldn't be focused.
Okay, fair enough. Now we run into a whole another issue of the human observer, because really what I'm calculating is where's the position of the images. The next question. Yeah, the next question is, would you be able to see it? And I think what you're saying is something like this, since it hasn't been formed, it's the light's coming to me, and the image isn't going to be formed until it's out here. I probably wouldn't see that one either. Right. So it's more complicated.
You would just see yourself at equal distance from the mirror.
Right. And if I turned around and looked over this way, I still wouldn't see that image because the light's going that way. Yeah. So I would, if I stood between these, I probably would not actually see that. So maybe my terminology is not well put. What I really mean is somebody standing on the outside trying to figure out where all the images are. And you wouldn't see them because they're ricocheting in here, but that's really what I'm saying. Where are all these images versus seeing them? Yeah. Okay. Because, yeah, and then of course we can add to this, because now you might say it's more complicated than just saying, oh, I don't see it because it didn't form, which was kind of my first answer to you. But it gets more complicated because I may see it because the light that then comes into my eye forms an image as it goes through my lens, so it gets reformatted. And it may, the ultimate goal for me to see something is, can I form an image on my retina? That's the ultimate. And I may be able to do that, or I may not, depending on where the lens of my eye is placed and how strong the lens is.
I guess you could go further and say it doesn't even matter if a human observer can see it, because there's many other applications for images.
Fair enough. Fair enough. And of course, that's what we're doing. I'm just trying to show you how to calculate. So again, I'm glad you brought this up. If this makes sense to you, you'll probably have an easy time in this chapter, because this is where it gets hard, where you have not just one mirror, but multiple mirrors, and keeping track of positives and negatives, and keeping track of image distance 1, image distance 2, image distance 3, object distance 1, object distance 2, object distance 3, focal length 1, focal length 2. If you keep all those straight, you're good. And so the real key here is right here. Remember these. And remember the image from the first mirror becomes the object in the second one. And then you just do your calculation. So as I do my calculations, let's see, how far did we get? We have found the image now from the second mirror. So let's do this calculation yet again in the orange for the third one, and we'll stop there. I don't think there's any point in going to the fourth or the fifth one. We better move on to lenses. But when I get to here, I can then say, well, I'll start with what is my focal length. Well, that's still the same. I mean, that has to do with the curvature of the mirror. And just because it's ricocheted around, that's not going to change here. So the focal length is still the original 15 that I have since erased. But what's my object distance? What's the P? Well, remember, from the second mirror, this Q was a 5. And it was a positive 5, which meant what? The image was 5 this way, right? So how far is it to the mirror? 20. And would it be a positive number or a negative number? Yeah, in this case it's a positive. The image actually got formed right here before the light got to the mirror. Okay? Had it been such that the image would have been formed back here, then this extra distance would have been the P and would have been the negative P. But this one does have a positive P. And so then I can get my Q. And so my Q for this case, and out looking at my drawing seems to indicate that my Q should be positive or negative. It's positive, right? It actually reflected off and made a real image there. It's on the real side of the mirror. So if I've done this right, I've got 15 reciprocal minus 20 reciprocal, and then the reciprocal of all of that is my drawing's way off if I did my numbers right. Anybody else get 60? 60? Okay, I think I did my numbers right. My drawing then is really bad because 60 is way out there. So this is out here. Okay, right here. Okay. So there's yeah, something like that. Okay. And then as I heard somebody say, if we're going to do this a fourth time, as it goes into this mirror, then we're going to have a negative P. And then so forth and so on. Well, like I said, we better stop because there is lots more to cover in this chapter other than just the mirrors. But it is definitely worth looking at those mirrors. And you probably have noticed this whole time, I've deliberately tried to keep these drawings up and center because just like we did a flat mirror, a concave mirror with 3 options, and a convex mirror with only 1 option, we will see exactly the same thing for the lenses. So let me put the optics back up here. Let me pull out, instead of a mirror piece, let me pull out, what might be a good one? How about this one? This shape. Now, what's different here is the light is going to come in and bend when it hits here. It's going to bend again here. What I will see is the overall bending of both surfaces. If I turn off the room lights and place it here, what do you notice? Doesn't this look a lot like this? Of course, it goes through it because we're refracting. And that's the point I tried to say on Tuesday when we got started. The point of the learning about reflection and refraction is those are our 2 options to control light. And so the first half of this chapter was all about reflection. Controlling the light through reflection. And learning where the images will be and how to do the calculations. Because the second half of this chapter is this. A second way of controlling the light is with refraction. And the refraction, of course, has Snell's laws in it, and that's a little harder geometry. And we'll go through the geometry if we still have time today here. But more importantly than that is to realize that the end result of something with this shape brings the light to a focus. If I turn this back on and maybe draw these rays, here's what they would look like. I've got 5 rays coming in, hitting a glass surface. As they hit the glass, they will bend towards the normal. Fair enough? And so if the center of curvature, or the radius of curvature of this is something like this, then when I draw a dotted line out here for the normal, which way does the light bend? Towards the normal. This one, I will say, is down the middle, so it doesn't bend. This 5th one down here at the bottom bends just like that one up there. These in between the top and the bottom one are going to also bend towards the normal. And so that first surface creates something that looks like that. The light begins to converge. Now, of course, the lens, I think, gets a little more complicated because guess what else happens? We have a second surface. And so now there's going to be bending and refracting again. But this time it goes from the glass into the air, so it bends away from the normal. And when you draw the normal here, away from the normal is down still. So there's some bending when it comes in, and there's some bending when it comes out. But they're both down, at least for the upper beams. The lower beams would bend the other way. And so what you end up getting is a focal point. You get all the light coming to one particular point. And that's what this, a little experiment is supposed to show. That this lens behaves like this mirror. Of course, now, what kind of mirror did we call this? Concave. What shall we call this? Convex lens. Oh. And what we'll see is everything we've done for the mirrors works for the lenses, but they reverse roles, and that's just a recipe to get yourself confused. So the convex lens and the concave mirror each have what we're going to call a real focal length. They really make the light converge. Did I see a question? Yeah.
Why not call that a concave lens if you look at it from the perspective of the
I like this terminology better. It's not what your author chooses, so I'm gonna follow your author. But your author does the geometry shape. Something that's curved in, right, is where the bear sleeps in the winter, so it's concave, right? So this is the concave shape, and this is the convex shape, something that bows outward. So your author has chosen that. But I like, this is a positive mirror. This is a positive lens. And that standard I like better. I don't use it, but that's what I'm actually used to. That's what I learned on, and that's, you know, when I spent 10 years in an optics lab, that's what we always did. It was like, you know, do you have a spare positive lens? Do you have a spare negative lens? Right, you know, or we would order a positive 15 centimeter lens, meaning a positive focal length, meaning convex. There's also some other issues too, like talking about the geometry. I don't think it's a good idea, but positive and negative is, yeah.
Can you think of a lens as a combination of mirrors?
No, I wouldn't.
So how would you compare them?
Well, my comparison is this, that they both have what I would call a focal point. They have a real focal point. They really have the light converging to a point. So in that sense, they're the same. And in that sense, guess what we're going to come up with? The same sets of equations. And so as long as we stick to the same rules, we just need to be careful, because here, and you can see why they're different, in the mirror, the light reflected. In the lens, the light refracted. So guess what we're going to call the real side of the lens? Where the light really goes. Which is which side? This is the real side. Because the light really went there. And so if we're not careful, we will mess up our knowledge of positives and negatives. Because look at this. This is your chart that your author said, use this sign convention for mirrors. Let's look at the sign convention for lenses. If we scroll down, I think that's table 3 here. Sign convention for lenses, thin lenses. When is, or maybe I'll go to the focal length. When is the focal length positive? When it converges. Well, that's maybe not a good way to phrase it here, but okay, maybe I'll come back up here. When is the image positive? When it's where? On the back of the lens. Why? Because that's where the light really went. So I think that's the best way to remember this. The positive side is where did the light really go? It works for the mirrors, it works for the lenses. Of course, the difference is for the mirror, this is the positive side for the image, because this is where the light really went. Hence the name mirror, it reflected it. But where's going to be the positive side for the image in the lens? This side, because that's where the light really went.
It's still real because it's actually
And it's still real because that's where the light is really going to go. And in fact, let me draw a picture over here. It's the whole reason I wanted to leave this picture on the board here. Because if I now draw underneath it a lens, and I put, say, a focal point right here, and I put a little dotted line, and I put an object that is some distance p from the lens, and I draw a ray that goes parallel to the optical axis, and I know it actually bends going in and coming out, but be okay if I just kind of bend it in the middle of the lens. That's not really what the light does, but will it be okay if I just put a little dot there and then say, where does it go from here? That's where that light goes, right? Goes through the focal point. And so do you kind of see how this one looks like this one, yet kind of different? Maybe if you imagine the light came in and bounced back, and you took the light that bounced back and you folded it over. Isn't that what this is? That's what I'm trying to get you to see. And when you can see that, you will make this chapter much easier on yourself. You will begin to see that the positive lens, the convex lens, and the concave mirror are exactly the same. And just like the concave mirror could make an image that is upside down and smaller, an image that is upside down and bigger, an image that is right side up and bigger, this convex lens can do those same three things for exactly the same three reasons. And this equation will do exactly the same. We are going to have to follow our sign chart correctly for this to make sense, but an easy way to remember it is, again, the positive side is where did the light really go. And if you can keep that in mind, I think you can keep your sign chart well, and then you can remember that the equation that you're using for mirrors also works for the lenses. And then you can just kind of plug and chug, yeah.
So if you have a mirror, your focal length is always going to be the same no matter what kind of mirror it is.
Oh.
If you have a lens, it's going to be different depending on the material, right?
Yeah, now, of course, mirrors and lenses have a lot of similarities, but of course, they have some differences too. And you just touched on one of them. I don't know if you guys heard this. Let me talk more about lenses before I talk about the focal length. But we learned that the focal length was half the radius of curvature for the mirror. What we will soon see for the lens is the focal length is much more complicated. It has to do with the curvature of the front, the curvature of the back, and the material it's made out of. And so the formula that we are going to get is going to have a radius R1, a radius R2, and an index N of what it's made out of. So much more complicated, yes. And so let me come up to it, and I'm whiting that for the end, but at least you can see that it does have a focal length. And if you know the focal length, then you know everything else about it. You can know where is the image, what is the magnification, and if you send the light into another lens, you can then get the final image from the second lens, or it goes from a lens to a mirror to a lens to a mirror, and we can calculate where the final one is. And so that's where I want to get started here, that you see this picture. Now let me keep drawing. Hopefully you'll see the analogy, because this part that I've drawn so far really is analogy to this ray. This ray that hit the mirror and bounced through like that. That's this one. Where's the second ray? Well, again, up here it was the one that hit the focal length first, then the mirror. How are we going to do that with the lens? And hopefully you can see it, that a lens, you might say, in this sense, is different. It has a focal length on both sides. Now, you might say the mirror is kind of the same, because the mirror really has a focal point before the light hits the mirror and a focal point after it hits the mirror. It just happens to be the same point because the light reflected back on itself. But if I take this lens, and before I move the lens, let me make a little dot there where the light converges. Let me mark where the lens is so I don't move its position here. But what if I pick this lens up and turned it over? So in other words, the light's going the other direction, right? What do I get? Same thing. And you'll see that in the equation when we figure out, but the point is, it depends on both curvatures. And it depends on the index. And so it really doesn't matter which curvature it hits first. It ends up with the same focal point. And so as you have said, or somebody mentioned, that to think about a lens, I really need both focal points. I need to realize there's one on each side. There's really two, and that's, like I said, kind of similar to what we did with the mirror. We didn't really call it two, but we did say there was one that it passed going in and one when it passed coming out, and that's what I'm trying to say here. There is one focal point going in, one coming out, and they are the same number. That's why it doesn't depend on the radius of curvature. It's not like this one depends on this radius of curvature and this one depends on that radius of curvature, which I often get students asking about. No, that's not what the focal point depended on. The focal point depended on the bending at both surfaces and the index of the material. And so when you switch it around, it still goes through both surfaces and through the material. No, okay. And so those focal lengths are the same length. And that's why I think this makes a good example. In fact, let me change it here. With this focal length on here, let me get away from this lens and change it to this lens. Do you see anything different? You're looking at the back side, so maybe I should turn it around here. Is there a difference between these two? Besides the number. Yeah, with this one, which one was I using? To the two. Okay, I was using this one. But what I want you to see is this one is less curved. Right? It's got a less bow. Now, what you might not be able to tell is it's the same material. It could have been a different index, but it's not. They're made out of the same material. But what I want to illustrate here is they are made out of the same material, but they have a different bow to them, a different curve to them. So this shape will still converge the light, but what will be different about it? Yeah, it should be a longer focal length, right? Because the bending is determined by the angle it comes in. And what we learned in the last chapter is the amount of bending depends on how big the angle is. And so something that's curved a lot comes in and it hits at a big angle and it's going to bend the light a lot. But something that looks like this is going to bend it very little, and something that looks like this. Oh, wait, that's the mirror. This. There's no curvature to it, right? So if I were to put this one up here, you hopefully won't be surprised that it doesn't bend it. But what you hopefully, maybe I should have put it in the same spot. And so there's no focusing to that one, but there is, here's number one, a focusing of this one. But what do you notice? A little bit further out, exactly. So again, just kind of giving that gut feeling. I haven't given you the equation yet. Hopefully we will get there. But that equation, of course, would I expect the focal length to depend upon the radius of curvature. And so the conceptual side here is you're going to get a different curvature. And I think we even have a very little curved one. This is so little, it's almost even hard to tell. But it does have just a little bit of curvature to it. And it does give me a focal point. It's just way out there, yeah.
What if the curvatures on either side are different? Then you have different...
All right, getting a little bit ahead of me. But remember, the bending occurs on both surfaces. I don't have a good example of that. This might be close. Let me just block two beams so you don't get confused with something else. But I'll take two beams and put something, as you said, here. What will happen? It'll still focus it, right? Because remember, the bending is at both surfaces. So in this case, I have one surface that has no curvature, so no bending. But I have another one.
What if you switch it?
Well, again, it'll bend at one surface, but not the other. Okay. Right? And it's the same focal point. So it doesn't matter which way I go, I get the same focal point. But I will say this then, and of course this one has a small focal point because this one has a lot of curvature. In fact, I would argue that the curvature of just this one side outperforms the curvature of both of these sides. You know, and so as you'll see here, it's both curvature. So even something that looks like, you know, like this is why we call it a plano convex lens, a double convex lens.
What happens if you don't block the bottom?
Well, remember the approximation we did with our mirrors? If our lens gets too big, we get areas that are beyond small angles. I blocked it so you wouldn't ask that, but okay. But you will probably, oh, that's not too bad. Because this one actually has total internal reflection here. The angle is so big it's beyond the critical angle. And so only these three come out anyways. And if the curvature wasn't as much, then it may get out, but what would happen is these two ones would hit at a different point. And that would make a terrible lens because not all the rays are controlled the same way. And so part of the image is focused different than the others. For those of you who are into photography, you know this by adjusting your aperture. You want a nice, clean picture. What you do is you put a small aperture. You open that aperture just a little bit with the idea that if your lens is this big, you only let the light come through right there and everything hits at a small angle. Now the bad part about that is you don't get much light. So trying to take picture with quality in the dark is difficult because now what you want to do to get more light is open it up. Now as you open it up, you hit other parts of the lens that don't actually have the same focal point, and those far edges get a little bit out of focus. Unless you start making a lens that is not in the shape of a sphere, but is in the shape of a parabola. You're going to pay for that. And the manufacturing of that. But you have to compensate for the fact that the rays further out would be a little bit different. All right. Well, like I said, that's why I was... But that was interesting, though. I didn't think they were going to have total internal reflection. I just thought they were going to have a different focal point. Yeah. And all right. Well, back to this now. So let's draw this second ray. All right. So where's this second ray? Good. And so now I hope I convince you that there's a focal point on each side. And so what I would have is it would go through, it would hit the lens, and then it would go parallel. So those are the two equivalents of these. Where's the image? Yeah. It's right there. And I don't know if my picture shows it quite well enough. Is that one smaller than that one? And if you are more than twice the focal point, which in the mirror we call that the center of curvature, but for the lens that doesn't really have a meaning anymore. It's just twice the focal point. But if I do twice the focal point like this one, I should get an image like this one that's upside down. And that's formed but beyond the focal point, but shorter than twice the focal point. And that's what we have. Upside down, smaller, and in between those two dots. What do you think I would get here? If, again, I took my two focal points and I put my object there. And like we have here, you will hopefully see the same here. They will reverse roles in the sense that the light that goes here will go through that focal point. The light that goes through that focal point, in this case, it's not really going to hit the lens because I didn't draw it big enough. But if it's okay with you, I will either draw the lens bigger or say, well, even if that ray doesn't go, these other ones do. But this one is the one I know to draw. So then I will draw across here, and I will get that. And so twice the focal length is here, and so my image is here. My image is upside down. My image is bigger than my object, and it is further away than twice the focal length when this one is in between. And so just like we saw there, we also see here. Fair enough? And I haven't bothered to do the triangles, and in fact, let me not do the triangles. I will tell you. Guess what they come out to be? Exactly the same equation, if you're willing to follow this sign convention. So just like the mirrors, if you remember, in the mirrors, at this point in our discussion, we called the P and the Q positive and the H negative, right? And we really have the same thing. In this scenario, if this is P and this is Q, this is a positive P, this is a positive Q. And again, the best way for me to remember it is the Q is not whether it's left or right of the mirror or lens. The Q is positive when the light really goes there. So if the light comes into a mirror and bounces off, and maybe I should say comes in from the left, goes to the right, then when it bounces off and goes back to the left, over here to the left is positive. But if the light had been coming in from here and bouncing off, then over here on the right would be positive. The positive Q is where the light goes, which depends on whether it is a mirror or a lens or goes from the left or from the right. And then I don't have to worry about left or right. It's just positive Q is where the light goes. So in a lens, the positive Q is the opposite side because the light starts over here, goes through the lens, and this is the positive Q. If the light had been going this way, then the light would go over to here and positive Q would be on this side. Fair enough? Because the light would start over here and go over to here. And so you will see, hopefully, in here that we have the same idea about positive and negative H's and positive and negative Q's. And our negative Q is what we would call the virtual. And so far I haven't drawn that one, but that will occur here. If I take this and kind of clear this up a little bit and draw it here, what would the equivalent of this one look like? Well, I guess I would have the lens here, dot, 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 dot. I will put a focal point here and a focal point here. And I will put the object in front or closer than the focal length. And that's what I have here. And if I draw these rays, let's draw this first one. I think this is the easiest one to draw. If I draw a ray that goes parallel, in the mirror it bounced off and went through the focal point. In the lens it does what? It bends and goes through the focal point. Where's the other ray? See this one? We were drawing it from the object hitting the mirror as if it came from the focal point. I'll do the same thing. I will draw a ray that is going to the lens, coming as if it is from the second focal point. And what will happen to it when it hits the lens? Okay, good. You guys are starting to see the analogy. It takes a little while to see that these are the same thing. But that is the direction of those rays. And somebody standing over here would trace this one back and trace this one back and say that there's your image. And your image is what? Bigger. Right side up. Just like we saw here. And just like we said here, Q would be a negative number on this side. Isn't this where Q is a negative number? The light's not really coming from that side. Or, excuse me, the light is not really there forming the image. The light from the image, the light really went here. It came from over here from the object. It went from over here, but it never really converged at this point. And so hence, negative. Exactly the same geometry, exactly the same math. I just need to keep track of positives and negatives. And like I said, for me, it works best for my Q's when I think about, okay, the positive Q is where the light really goes. So for the mirror, that would be the positive. If the mirror was the other way, that would be the positive. For the lens, if the light goes this way, this would be positive. If the light was going this way, this would be positive. Where does the light really go? That's the meaning behind this. Yeah.
So we have the light bending in the center of the lens, which is for shorthand?
Yeah, shorthand.
Okay.
Yeah. Good point. I'll say it again. I've drawn it bending in the center just because shorthand, it actually bends twice, and I just didn't want to draw it twice, yeah.
Isn't it kind of negligible since it's in
Oh, well, okay, but it's still bending twice. Once when it goes in, once when it goes out. The derivation of the thin lens comes in because we're going to see here, we're going to treat those two surfaces as being identical points. And when we do that, we will come up with a really nice equation for the focal length, which I haven't done for you yet. But the focal length and the focal equation is valid for thin lens. And of course, any lens really isn't infinitely thin. There's always a size to it. But if you're looking at big distances, you can say it's relatively thin. And in fact, this is where I want to pass it around. I've got some lenses here that I'll pass around. Here's a pretty good size convex lens. Here's a huge convex lens. Okay, but this convex lens, I don't know if I'd call this one thin, but this one I would, right? So here's my thin convex lens here. Now maybe I'll just do a couple of them. Might be nice to have different curvatures to them. Yeah. So that this one, although it's smaller in diameter, has more curve to it than this one. And so the focal lengths are different. And I would think that this one has a smaller focal length. But as I pass them around, play with it and try all of these scenarios here. Try this scenario, which I'll start these around. The big one is for me to hold up and you can see a little better, but I might look at that door. This would be an example of, does this form an image of something far away? And so as I look at that door, it sure does. It's upside down. The back of the room, upside down. I don't know, am I upside down? Can you see me? This one might be better. Yeah. This one's so scratched. I don't know. Can you give me a light through there? What's this one? No, that's a negative lens. Well, anyways, but try your different options. As I look at that door, definitely smaller, definitely upside down. Okay? As things get closer, maybe here. And like I said, this is the one that it's kind of always hard to see right here because it's bigger, yes, it's upside down, yes, and it's getting close to your eye, and it might be so close to your eye that your eye can't focus on it. And as I said, this is the kind of thing you would see if you looked at some writing on your calculator or your pencil or your paper. If you bring it closer, 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 whoa. At some point it's going to get blurry because your eye has to bend that, and your eye can only bend so much and run out of strength here. But like I said, this is fairly good to see. And so as I look at that sink, yeah, that's probably pretty good. It's kind of best my eye can get it into focus. But I can see the sink bigger, and I can see it upside down. And of course, I think most of us are probably familiar with lenses like this, where we look at this scenario. What does this scenario do? It makes it bigger and doesn't invert it, and that's the kind of thing that you've probably used this as a magnifying glass, and you've come along and you said, okay, let's look at something in detail. And you'll adjust it right near the focal point. Huh? Yeah, so to use this well, like a magnifying glass, you really want it close. Because what you want is you want to be within that focal point. You know, I can't magnify the back of the room holding it here. It's why I might point out a telescope is not made with one lens. Because you can't get the lens close to the moon to focus on it. What you have to do is use the first lens to make an image of the moon. Then the second one to get close to that image to magnify the moon. And so you need a two-lens system for it to work. Binoculars, the same thing. You need an objective lens and an eyepiece lens. That's the logic behind it. But then again, pass that around and you'll see it as you get, for whatever reason I always use my watch. You can see it getting bigger and smaller, and then as you get further, it's upside down. And as you get really far, it's upside down and smaller with your different options. Okay? Well, let me keep going, at least as far as I can here for today. What do you think the next case is here? Got to be as similar to this. So, coming back to my little array box here, grabbing a lens that looks like, I don't know, can you tell that one's curved inward? And again, for namesake, what do you think we're going to call this one? Concave. This is a concave lens, double concave if you want to be more specific, as opposed to, which you're going to ask me again, I know, is it's a plano convex lens, okay? But again, looking closely at this, you will see that it does bend the light then the other direction. It makes the light diverge. Just like this convex mirror made the light diverge, this concave lens makes the light diverge. If we go back to drawing our pictures, what we would have is at that first surface, we would draw the 5 rays, and going into the glass, it would bend towards the normal. Well, in this case, the normal is up for the top one. Towards the normal is down. Towards the normal is down. Now, maybe not as much as this one. This one is probably just hitting straight through. This one bends towards the normal. But I'm hoping you'll see, like the other one, that you're going to get some bending as it goes in at the first surface. But also, second surface, going from the glass into the air, you're going to get a bending away from the normal. So in this case, away from the normal is more divergent. So both sides do bend it, and both sides do diverge it outward. That's a mess. But hopefully you saw as I was developing the picture that it is going to bend on both surfaces. Now I only draw it as one bending, but they do bend on both. And of course, the total bending is both surfaces, so it has to do with the curvature of both surfaces as well as the material, just like the convex.
So, since we don't see like a specific focal point, would you say it's virtual or?
Right. So I'm hoping that you see these similarities between this, where the light is spreading out after going through the lens, and that, where the light is spreading out after reflecting. And we called this a virtual focal length. So guess what we're going to say about that one? It too has a virtual focal point, and so it too can have a focal length that is a negative number, and it represents when we have a diverging lens. So a diverging mirror or a diverging lens has the same properties. That is, it spreads out. Geometrically, they're designed different because one's reflecting and one's transmitting. So the one that diverges is the convex mirror. The one that diverges is the concave lens, but they still behave in that same pattern there. Now, the other one, as I'll see if this one works too. I don't think this one's big enough to get all 5 rays. but at least I can get 3 of them. Maybe 4. Can I get 4? Yeah. And so maybe I will look at just 4. But again, you'll see it diverges out. Now, of course, in this one, there's no bending on that first surface because it's a flat plane, and then the bending's on the next one. But again, as long as one of the surfaces is curved, it will bend. And it doesn't matter. Well, I was getting that bump on there, but maybe I should block 2 of them like that. But you'll see again, it spreads out. And it actually has the same spread to it. If I were to measure this focal length back to here, it's probably somewhere around there, right? In fact, I don't know if you guys can see the dim light, but there's actually a reflection off the curved surface here. There's a kind of a concave mirror effect. I don't know if you can see some little rays in there. Maybe it's best if you don't. But if I turn it around, again, see how they come back here. So this is going to be referred to as, again, the focal length of this. Again, we'll just call it a negative focal length or a virtual focal length. And again, not that we mean the distance is actually a negative number, but in order for it to work out in all of this, and so we only have to have this one equation for all of our mirrors and all of our lenses, we just got to follow the rules here, and it will, and it'll work out perfectly. And so like those examples I was doing, we can see the calculations, and then we can just do our calculations as we go through our different lenses. And we'll say, where is the final image? Okay? So let me then see if I can draw this and see if this kind of makes any sense. If I were then to put a double concave mirror lens here, what I would say is right here is a focal point, okay? And the focal point would be on both sides, just like it is here. Not that one side is bigger than the other, because again, the bending is both surfaces. So whether I go from one way or the other, it goes through both surfaces either way. And I get the same focal length. But what I think is kind of interesting, or hopefully analogous to, is let's see what I will get. And you will get, as I called it before, the boring mirror. You always are going to get what? Virtual image, smaller, right side up. And so, let's draw those rays. So, if I were to draw the ray that went parallel and hit the lens, where does it want to go? Where does it go? Right, that's the whole idea of this virtual focal point. That was this diagram I was trying to get. This would then look like that. And to me, I think this is the hardest of all the rays we've drawn. Although maybe it's just as hard as this one here. Well, how do we draw the second one? Yeah, good. Heading towards this focal point. Right? We've already thought about this focal point. So let's think about this one. And so as we draw it heading towards that focal point, what's it going to do? Yeah, bend and go parallel. It's the reverse, right? Go parallel. So again, the one that goes parallel bends up as if it is coming from the focal point. The one that's already coming inward bends away as parallel because it was going towards the focal point. And of course, my question for you would be this. What is this person over here going to perceive? Right there. And again, I hope that looks very familiar. That's why I spent so much extra time on the mirrors, with the idea that maybe we don't have to spend so much time on the lenses, that you can see that they're really the same thing here. This is right side up. This is smaller. This is virtual, right? It's on this side where the light does not go. The positive Q is this side for the lens. Yeah, this side for the mirror. So this side is negative for the Q, for the mirror. This side is negative for the lens, where the light doesn't. And so it would be smaller. So I'll pass one of these around here. And maybe I'll try some different ones. Oh yeah, here's two good ones. They've got different curvatures. They look like they're both planes. Yeah, so they're both a plane on one side and concave on the other. But this one's got a lot of curvature to it. And as it makes a lot of curvature, this should diverge more. And of course, as it diverges more, it should make things look smaller. And so as you pass this around, look at anything. Look at something far away. Look at something close. It'll always be right side up. It'll always be smaller. And that, like I said, for one of these, I always look at my watch, but that is really small, and that is tiny, 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 tiny. And so I always get something smaller. Now, with that said, if I hold a big one up, here is a big one. This one might be kind of hard to tell it's concave. I don't know, can you? Okay, so do I look smaller? I'm definitely right side up, right? Okay, so I'm right side up and I look smaller. Of course, like the mirror, what the good advantage of this is it gives you a broad angle, right? And this has an interesting design. Let's see if I can show you the picture. I think the cleverness of it, it's referred to as a Fresnel lens, is pretty clever. Instead of making a big, fat lens, Fresnel had a creative idea. And of course, this shows a converging lens. But he says, why make a lens with a big curve? The bending only occurs at the surface. So if you were to cut this piece off and put it here, and cut this piece off and put it here, and cut this piece off and put it here. And in other words, why make the lens so fat and heavy and expensive when you can just cut the pieces? And so if you want to feel this, we're kind of out of time, but that's what they did, is they just cut it and they put the pieces here. I think you can see it a little better with this Fresnel lens. This one isn't very clear, but it's supposed to magnify. I don't know, do I look bigger? Okay. That's pretty crappy. But anyways, these are these old Fresnel lenses. If you've ever visited old lighthouses, that's how they build them. A big old lens in a lighthouse would be way too heavy to lift up and mount in there. And so you cut out most of the glass and only use the surface of it. And so you have your Fresnel lens with it. Also, I guess I kind of ran out of time. Maybe we'll talk more about this on Tuesday. But I love this picture. Partly, I guess, because I'm nearsighted. But for those of us who are nearsighted, which most people are nearsighted, take a close look at these two pictures. This one, look at those person's eyes. Look closely. Now, watch this. Look at this person's eyes. It's the same person. They do have different glasses. Here, they are putting on glasses that would fit farsighted. It converges the light. So what would happen to an object behind it? It would look bigger. But somebody that had a different lens, in this case nearsighted, what would their eyes look like behind their glasses? Smaller. And so you can see the effect. And if you look at somebody's eyes real closely, you'll know whether they're nearsighted or farsighted. Although I guess you don't really know how big their eyes are. But people like us who are nearsighted, I mean, we always look like tiny, beady, mean people. You know, we got these little tiny eyes, and the light, and you can even see the light go through your lens. You'll see it spread out. It almost looks like I got sunglasses or something, because as the light hits there, it spreads out. And of course, since it spreads out, there's kind of a shadow effect here. And of course, there's a light on the outside. So I'm clearly nearsighted. I can see that by diverging of the light. All right, well, good luck on the homework. There's a lot still to do.